Hello and welcome. This is a video on how to apply VSEPR theory or VSEPR theory. Students that I've taught before get to understand the basic principles, but then they find it quite difficult to do in practice and they make the same mistakes. And hopefully this video will go through the foolproof way of doing it. And if you follow this step by step, you will have no problems with this at all. You'll get this spot on, albeit you need to practice it in order to get it perfect. This will tie in with students who are doing A-level and in particular those who do in the IB, because I do the direct curriculum link to it. Now this is the first of many videos I do on VSEPR theory. I'm only concentrating on 4 electron domains and I'm not going anywhere near ions yet. In future videos I will tackle those things. So the link to the IB curriculum are from the following descriptors under application and skills. It's part of unit 4 and in particular 4.3. So the first thing is what you need to know is the deduction of Lewis or electron dot structures of molecules and ions showing all valence electrons for up to 4 electron pairs on each atom. Notice I put and ions in yellow to denote the fact that that will be in a later video. The next point is the use of VSEPR theory to predict the electron domain geometry and the molecular geometry for species with 2, 3 and 4 electron domains. We'll cover that today. And finally, the prediction of bond angles from molecular geometry and presence of non-bonding pairs of electrons. So hopefully this video will cover how you can do these things. So there's many steps that you need to take in order to deduce the electron and molecular geometry and bond angles. To remember the steps, I like to think of a mnemonic to help me remember. And the one that I use is Dirty Vinny bit my dust early morning. You might be looking at that and thinking, it makes no sense, what's he talking about? Well, I'll go through what each letter stands for in my mnemonic. So the D for dirty stands for diagram. The first thing you want to do is you want to draw a diagram of the molecule that you've got in as most accurately as you can. It doesn't have to be super accurate, just a rough idea, it shouldn't take you long. The V for Vinny is valence electrons. After identifying the central atom, you want to work out how many valence electrons that would normally have. The B for bit means bonds. How many single bonds is your central atom making? So it's gaining 1 electron from each because they're covalent bonds. The M for mi stands for multiple bonds. You have to take into account the multiple bonds and subtract them from the number you had before. D for dust, it means divide for electron pairs, which I'll cover in a moment. And then the E and the M stand for electron geometry and molecular geometry. Now these may not make much sense as they stand at the moment, but it's going to make a lot more sense once we go through some examples. So we'll start with methane, which is CH4. The first step, which is the dirty, is diagram. So the first thing I'm going to do is I'm going to draw what it should look like. So methane, I would assume at this point that carbon is in the middle. So I'll put a C there, and my hydrogen atoms will be either side. Now from just a brief glance, I can see that this is going to work because carbon needs 4 bonds to be happy. So that looks good as an initial guess. Now the V for Vinny means valence electrons. Now this is only for the central atom, not for the hydrogens. They don't matter. We just want the geometry around carbon. Now if you look at the periodic table here, I've kind of cut out the transition metals. If I look at carbon, you can see that it's in group 4. That means it must have 4 valence electrons. I'm going to start with 4. All right? My next step, B for bit, means bonds. Now if I look over here, I can see that it's making 1, 2, 3, 4 bonds. Okay? So what I do is I do plus 4, and then that'll equal 8. All right? Next step is for multiple bonds. Now in methane, there are no multiple bonds because it's all just single bonds. So that step I can skip. My next step is to divide for electron pairs. Now basically I need to half it. So if I've got 4 electrons here in bonding, that must mean that I have 8 divided by 2, which equals 4 electron pairs. Effectively what that means is I have 4 electron domains. Now up to this point I will expect that you have some understanding of the different shapes that you have in ideal molecules. After knowing that you've got 4 electron pairs, you should be able to establish the geometry. So carbon is here. Now if I've got 4 electron pairs, there must be 1 there, 1 there, 1 here. I'm going to do the wedge to show that it's going towards me, and 1 there to show it's going away from me. Now you can see that my electron geometry has to be tetrahedral. Okay? Now my next step is molecular geometry, and that's for the morning part. Now, if I think about it, I've got 4 hydrogens I have to put around this carbon. So 1 has to go here, 1 has to go here, 1 has to go here, and 1 has to go here. So my molecular geometry is the same because each electron domain is occupied by an atom. So that is also tetrahedral. Okay. To finish off, we're going to do the bond angle. The ideal bond angle for a tetrahedral molecule is 109.5. That's something you have to remember. Because I've got no lone pairs, it stays as 109.5, and that's my analysis done. Okay, so that's methane. Let's try another example. Now we've got PF3, which is slightly different. So first off, I've got to do my diagram. Again, from the outset, I'm not going to make any early predictions because that's dangerous. I'm just going to write P, F, F, and F. I don't think there's going to be any double bonding here because fluorine only needs 1 electron to be happy. Single bonds is all it wants to do. All right, so that's good for me. I now need to work out the valence electrons, and this would be around phosphorus. Now, if I look at the periodic table here, I can see phosphorus is in group 5, okay? So it must have 5 valence electrons. That's my first step. Next step, the number of bonds. 3 fluorines, there are 3 bonds, so it must be 5 plus, ooh, it's a bit of a clumsy plus 3, that equals 8. So I've got 8 electrons in bonding. My next step is multiple bonds. There are no double or triple bonds here, so I can ignore that step. Next up is to divide for electron pairs. So if I get my 8 from there, and I divide it by 2 again, that gives me 4 electron pairs. Okay, so I can now work out my electron geometry. This is my E for early. So P is here, 1, 2, 3, and 4. So my electron geometry, again, is tetrahedral. But I now need to work out my molecular geometry. Now for this step, I need to look over here and see how many fluorines I've got which can attach to my phosphorus. I only have 3. So 1, 2, 3 are occupied by atoms. The last one isn't. Now if it's not bonding to anything, it's just a lone pair. So what I'm going to do is I'm just going to get my eraser, I'm going to rub that out, and I'm going to replace it with a lone pair. And that is my molecular geometry. Now you can see that it's not trigonal planar because it's not in one plane. This lone pair is bending these all down. So instead, it's trigonal pyramidal. Now the bond angle always refers to my electron geometry. Do not worry about this when dealing with bond angles. We always have to go there first. It's tetrahedral, so it has to be around 109.5. Now because these lone pairs take up more space, they're going to push these down a little bit more, so it's a little bit less than 109.5. For the IB, you don't need to know the specific number, you just need to do the inequality sign and you're good. So that's my second example. Let's do a third. H2O. So again, I'm going to start with D for dirty. Diagram. So I'm going to assume oxygen's in the middle and I've got 1 hydrogen either side. Okay, that's what it's roughly going to look like. I now need to go for Vini, which is my valence electrons. Again, I go to my periodic table. I can see oxygen is in group 6, so it must have 6 valence electrons. Next thing's bonds. It makes 2 bonds, so 6 plus 2 equals 8. So I've got 8 electrons to deal with. M for my is multiple bonds. Now there are no multiple bonds here, so I can ignore that step again, which is quite convenient. D for dust is divide, so I have to get my H from here, divide by 2, and that gives me 4 electron pairs. So now it's time for early, which is electron geometry. So if I draw my oxygen here, and I've got 4 electron pairs, so it's going to be 1, 2, 3, and 4. And I can see already that I'm going to have a tetrahedral arrangement, so my electron geometry is tetrahedral. If you're getting good at this, you can also actually do the bond angle as you go along. You know it's going to be around 109.5. The question is it going to be smaller than that, and by how much? So I've got to do my molecular geometry now. So let's have a look at H2O. I've got 2 hydrogens on the oxygen. So I need to put 2 down. I'm going to put 1 over here and 1 over here. But that leaves me with 2 electron domains which aren't bonded to anything. They have to be lone pairs. So I could put that here like so, but that looks a bit clumsy. So just to tidy it up, I know I've got 2 lone pairs, so I'm just going to get rid of all these annotations, and let's replace it with my lone pairs, and there you have it. You don't necessarily have to have that coming towards you, you could just have that as a straight line, and that's how it's normally drawn. So my molecular geometry is not tetrahedral anymore, it's now bent. Okay, and it's certainly not linear because of those lone pairs. Okay, we're going to try one more example, which we're now going to introduce multiple bonds. And the example I've chosen is COH2, which looks messy, but actually, if you think about it, is not too bad at all. D for dirty is diagram, so let's draw it out. So I've got carbon, hydrogen, hydrogen, oxygen. Now to make this work, my carbon needs 4 bonds. So I'm just going to put another bond there, and that actually satisfies the oxygen as well, because that needed another bond to be happy. So that's what it looks like. You might have to sometimes play around to really work out what it should look like before you get on with doing the rest of your VSEPR analysis. My V for Vinny means valence electrons. So this is my central atom. Carbon is in group 4, as we've seen before. So it has to be 4. I now work out the number of single bonds. Now this is key. Single bonds. There's one here, there's one here, there's one there. I'm not going to consider this until later. So it's going to be plus 3. Now that gives me 7. Now my next step is multiple bonds. If you have any multiple bonds, be it double or triple, you have to subtract 1 for every single multiple bond you have. Now I have 1 extra bond here, so I'm going to do 7, take away 1, which gives me 6. So I've got 6 electrons to play with. My next step is to divide for electron pairs. 6 from there divided by 2 equals 3 electron pairs. So now let's get on with it. Electron geometry. Now my carbon's in the middle, as I know. Now if it's got 3 electron pairs, the geometry has to be a trigonal planar arrangement. Oh, I'm going to get rid of that, sorry. It's got to be a trigonal, there we go. It's got to be a trigonal planar arrangement. So my electron geometry, I'm just going to write it here, is trigonal planar. And that's good. Now bond angles we can actually do while we're here as well. So it's going to be somewhere around 120 degrees, you know, kind of 3 wedges of a circle. My next step is molecular geometry. We're at the final part now. Now I've got 2 hydrogens, which I'll put over here, and I've got 1 oxygen, which I'm going to put there, and I'm going to put a double bond. And that's it. So molecular geometry is also trigonal planar, because it matches with what you've got there. Those are both the same, bond angle's 120, and we are done. So hopefully you found this video useful. In future videos I'll do more work around ions, and then I'll move on to structures which have 5 or more electron domains. Thank you very much.